Galvanometer, we know. Galvanometer to detect current. See, you cannot use the galvanometer for direct measurement of current. It's only for the detection, because the it is very sensitive instrument. Sensitive instrument, for very small amount of current, it may produce a long deflection, or the larger deflection it may produce, and then for larger current the coil may get damaged. Okay, that is why galvanometer is a very sensitive instrument. So we cannot pass a high current through the galvanometer. So even for a very small amount of current, it will produce a deflection. Okay.
Okay.
And in that is why to measure the current, we need ammeter. And to potential difference, to measure potential difference, we need voltmeter. This ammeter, no, it is connected in series with the circuit. In case of a straight wire, it is cut into two, and that ammeter is connected between the two wires. Okay, it is not connected between the point, it is connected along the wire. And voltmeter is connected in parallel connection. So between 2 points alone, you can measure the difference in potential. In the same line, you cannot measure potential difference, it will show zero deflection. Potential difference means two different points have different potential values. Therefore, those two values are in parallel connection, so not in series connection. Okay. And the principle of ammeter as well as voltmeter, both the instruments should draw less current for their deflection. To get the deflection, see, ammeter as well as voltmeter, they are, I think, the conversion galvanometer only. The same pointer is present in these two instruments. Okay, whenever current passing through voltmeter as well as ammeter, again there is a deflection. Okay, in order, let's see, for that particular deflection, we only need very less amount of current. The actual current should not be, the entire current should not be used for these two instruments. Okay, the circuit should not be disturbed. The network should not be disturbed. Okay, the current must be very small. That we should keep in mind. So that is why the entire circuitry is having some different arrangement. And from galvanometer derivation, we know phi is directly proportional, or phi is equal to the constant k. K only we use in first class. The constant, yeah, k only.
Yes.
Phi is equal to, sorry, not k, NBA. Phi is equal to NBA divided by k into I. The entire things, they are constants. They are constants. We call them as galvanometer constant. Galvanometer constant, that is represented as sometimes G or some other constant. We may see this. Here they have not mentioned any special terms. Okay, in some other textbooks, no, they use the entire terms K divided by NAB, K divided by NBA, It is called as galvanometer constant.
Okay.
Galvanometer constant. It means that the deflection is purely depending on the current through the galvanometer. Okay, now we'll go for the conversion. So this point we should keep in mind. Okay, the galvanometer, sorry, ammeter as well as voltmeter, they should not disturb the entire circuit. They only draw very less amount of current for their operation.
Okay.
I'll go for ammeter. Already we told you ammeter must be connected in series. Okay,
Yes.
that you will see later. Ammeter, the conversion of galvanometer into ammeter. So that is the conversion of galvanometer into an ammeter. Maybe. For this particular case, a galvanometer of known resistance, a galvanometer of known resistance is taken. It is connected with another resistance. The entire arrangement is connected with another resistance called S, shunt resistance, in parallel. So this is a network. So we don't need to worry about the starting and ending of this particular arrangement. Okay. So the current I is coming arrangement. Current is IG. And we have connected a resistance S in parallel with the galvanometer. We call it as shunt. Shunt means parallel. Shunt resistance is a parallel resistance. And the current through the shunt is I minus IG. I minus IG. Okay. A galvanometer is converted into an ammeter by connecting a shunt resistance with parallel with the galvanometer. Here the resistance of galvanometer, we just look into the terms used in NCERT. Resistance of galvanometer is RG. Shunt, here they have taken it as RS, but you just go with the S only. So don't use RS. You use S.
Okay.
Okay, the resistance of galvanometer is RG. RG is resistance of galvanometer. It is known value. The same is we done with the figure of merit experiment. In practical, we did know figure of merit experiment. The resistance of galvanometer is measured using that method. Okay, then shunt resistance. Okay. What should be the value of this shunt? That is the question mark. See, suppose you are measuring a high current. Already I told you galvanometer is a very sensitive instrument. Okay, for very small amount of current, it is producing a larger deflection. Suppose if the current I is very larger, no, what will happen? The galvanometer may get destroyed.
Yes.
So in order to prevent this particular galvanometer from a larger amount of current, what they are using now, the shunt resistance with a very low value, very low resistance.
Also more current will go there.
Yeah, with the very low resistance means the more amount of current will flow through the shunt resistance. We know the tendency of current. Current will always take the path of low resistance. Okay, therefore the galvanometer is now prevented. Okay, the most amount of the only the fraction of current is going through the galvanometer. So Ig is a fraction of current. This Ig produces full scale deflection. Full scale deflection. Now we verify this equation. Using this equation, we'll go for the entire conversion. See, we have a small circuit, and we can go for Kirchhoff rule in this circuit, in this loop. Okay, see this. Also, this is a parallel connection. Either you can go for Kirchhoff rule, or we can go for a simple parallel rule. In case of parallel connection, the potential across galvanometer as well as the resistance are same. We know. So voltage across galvanometer equal to voltage across the shunt. Is it right? Therefore, you just apply Ohm's law. Applying Ohm's law, Ig into Rg. Ig into Rg equal to voltage across the shunt I minus Ig into S.
Yes.
Okay, I minus Ig into S. Then our aim is to find the value of Ig. Okay, just solve this equation. That is Is minus Igs. Here it is IgRg. Then take this to the left hand side. Ig taking common Ig. Rs plus S. Sorry, Rg plus S equal to I into S. And small arrangement. Okay, small arrangement. Ig is equal to S divided by Rg plus S into I. See, these terms are constants. The galvanometer resistance, shunt resistance. Actually, shunt resistance is taken for the full scale deflection. So appropriate value of shunt is added with the galvanometer to get the full scale deflection. So we cannot take any random value. So we have certain calculations. Okay, so if you want to have the range of the ammeter from 0 to 1 ampere or 0 to 5 ampere, to fix that particular value, we have to choose this shunt resistance appropriately. Okay. If we choose that particular value, then Ig will produce full scale deflection. And now see this equation. See this equation. All these terms are constant. S is constant. Rg is also constant. It means that Ig is proportional to I. Ig is proportional to I. Or I, otherwise. I is proportional to Ig. See, this current is the current to be measured. Is it right? The current to be measured is proportional to the galvanometer current. Current through the galvanometer.
Okay.
Do you understand?
Yes, sir.
And we know already we have defined the galvanometer current. This one is the galvanometer current. Okay, galvanometer current is directly proportional to the deflection. Deflection produced in the galvanometer. Therefore, we already know Ig is proportional to the deflection.
Yes, sir.
Therefore, the current to the ammeter or current to the ammeter is directly proportional to the deflection. This is the principle. Okay, we established Ig proportional to I. Already we derived the current through the galvanometer is proportional to the deflection. Okay, then the deflection is directly proportional to the current, actual current. That's all.
Yes.
So using this relationship, see this one relationship, you can construct the proper circuit for ammeter. And still we have one more thing, the resistance of the galvanometer, the effective resistance. Effective resistance of ammeter. See, the network is parallel connection. Therefore, the effective resistance of ammeter is equal to 1 by Rg plus 1 by S. Correct?
Yes.
Therefore, Ra, the ammeter resistance is equal to Rs into S divided by Rs plus S. Already we know S is very small. S is very smaller. Therefore, in case of parallel connection, we know if there are two resistors or more than two resistors connected in parallel, the effective value must be less than the actual value of the individual resistors. Do you remember? In
Yes,
case
sir.
of parallel connection, Rp equal to 1 by R1 plus 1 by R2. Rp must be less than R1 or R2. Okay, this is the
Yes.
rule. Therefore, Ra also must be smaller. Therefore, the resistance of the entire ammeter, the resistance of ammeter is very small. Very small. For ideal case, ideal ammeter, Ra must be equal to 0. Is that right? For ideal ammeter, the total resistance of the ammeter is 0, not the galvanometer resistance. Total ammeter resistance of the ammeter is 0.
0.
Next, already I told you, the ammeter connected in series, that is low resistance, that's all. And it should not draw more current. That is the main principle. The ammeter should not draw more current.
Okay.
That's all. So this is about the conversion of a galvanometer into an ammeter. So the case is, we are just connecting a very small amount of shunt resistance with the parallel with the galvanometer. So everything is done. And the second question, the continuation, conversion of galvanometer into a voltmeter. To a voltmeter. Again, the same rule. Same rule. The deflection is produced based on the current through the galvanometer. That deflection again is proportional to now the voltage. Okay, previous case, the current through the galvanometer is proportional to the actual current. Okay, the current to be measured. Therefore, the actual current is proportional to the deflection. Okay, now we are just slightly just changing the equations. That's all. And this conversion is done by connecting a very large resistance in series with the galvanometer. Okay, a galvanometer is converted. The conversion of galvanometer into voltmeter by connecting a very large, not very large, a large resistance in series with it. Okay, so when you connect a device in series with a larger resistor, no, okay, it won't be affected by larger amount of current. It will be in safeguard type. Okay, the current will not disturb the particular coil of the galvanometer, so it will be in safer state. In the previous case also, the total current, most of the current is flowing through the shunt resistance. Therefore, galvanometer is saved. Similarly, in this case also, you should not connect the larger resistance in parallel with the galvanometer. If it is done so, the maximum amount of current will go through the galvanometer only, not through the high resistance.
Yes, sir.
Okay, so the circuit must be constructed properly. Wire and series resistance. That's all. A galvanometer resistance Rg and is connected with the resistance R in series with it. R is high value.
Big.
So this arrangement is a converted voltmeter. Okay, then the current through the galvanometer Ig, again it is flowing through the R. And we are not measuring current here, we only measure voltage. Okay.
Yes.
And applying Ohm's law in this case, applying Ohm's law, what is happening? The potential across voltage across voltage between the network. Voltage between the network is equal to I into R, Ig into total resistance, Rg plus R. That's all. Rg plus R. Otherwise, Ig equals to V divided by Rg plus R. Already we know the resistors, they are constant. The value of the resistors are constant. It means that Ig is proportional to V. Or V, otherwise we should write V is proportional to I. V is proportional to Ig. The voltage across the terminals is proportional to the current through the galvanometer, that's all. So, and already we know Ig is proportional to the deflection. Ig is proportional to deflection. It means that the voltage across the terminals is proportional to the deflection. That's all.
Okay.
So this is the principle. So the voltage between the 2 points is proportional to, again, it is proportional to the current through the galvanometer. Again, in turn, it is depending on the deflection. That's all. It produces the deflection. So this is the conversion. And the effective resistance of the voltmeter, RV. RV is nothing but R plus RG. That's all. Here it is high. The resistance is high only, not small. The previous case it is small. Here it is high. Therefore, the current current Ig is proportional to voltage. Therefore, the voltage is proportional to the deflection. I told you the full scale deflection. Full scale deflection is due to the current through the galvanometer. And ideal voltmeter. Ideal voltmeter, RV is infinity. The voltage of the the resistance of the voltmeter is infinity. So ideal ammeter, the resistance is 0. Okay, ideal voltmeter, the resistance is infinity. And one more thing, the ammeter, already we stated, ammeter must be connected in series connection. You should not get confused. Only the shunt resistance is connected in parallel. Okay, shunt connected in parallel. The ammeter is connected in series. Here it is again the opposite case. The series resistance, the resistance, high resistance is connected in series, but the voltmeter is connected in parallel connection. So this is to draw. This is to draw less current. Okay, for ideal case, what happens now? The voltmeter, it should not draw any current from the circuit. Ideal case, but in practice, the very small amount of current is flowing through the current. What is that? Voltmeter, but still it has what is that? High resistance. The resistance is very high, therefore it will only draw a very small amount of current. Okay, so this is about the conversion of galvanometer into ammeter as well as voltmeter. See, in case of numerical problems, you always try to draw the diagram and the equation. So don't memorize the equation. So memorizing the conversion equations, it is useless. Okay, also it is difficult. At that time, you will get confused. Okay, see, in case of ammeter conversion, ammeter, see, there is a galvanometer and shunt. That's all. Shunt. Okay, this current I, and here it is Ig. This one is I minus Ig. That's all. Okay.
Yes.
Then Ig into Rg equal to I minus Ig into S. That's all. You solve this equation for your convenience. Okay, what quantity they are asking, it is depending on the given situation. For voltmeter, galvanometer is connected in series with R. Here it is Rg, the current Ig. Therefore, Rg plus R equal to voltage. That's all. So don't memorize the equation. It is easy to write the equation using the diagram. Okay, simply if you memorize this equation now, finally you will make mistake. Whether it is I minus Ig or Ig minus I, you will get confusion. Now we'll see some problem based on this conversion, then you will get some idea. Ammeter problem. meter. So again, so whatever may be the question, we'll draw the diagram. Okay, galvanometer. Galvanometer is converted into ammeter by connecting a shunt. Shunt, and this is I, and here it is Ig. Coil has resistance Rg is 15. Okay, and for full scale deflection, see, you have to be very careful. Full scale deflection, I told you, for full scale deflection, it is Ig only. 4 milliampere. Convert it into an ammeter range of 6
I is
6 ampere. 6 ampere. So we need to find the S value. What is S? So that is the question. So it is not directly given to measure the value of S. We have to convert the system into an ammeter of the desired value. Okay. So now write the equation. Okay, write the equation Ig Rg equal to I minus Ig into S. Here the current is I minus Ig. Is that right?
yes.
So our aim is to find S only. So Ig Rg divided by I minus Ig. So the value of Ig is 4 milli. 4 milli means 10 power minus 3. Rg is 15 ohm. All divided by I is 6 minus 4 into 10 power minus 3. 4 into 10 power minus 3. So the value shunt, it is around 0.01. 0.01 ohm. This kind of questions, we need to frame an equation and then solve for the solution. See, galvanometer is converted into voltmeter. Galvanometer into voltmeter. We know the diagram G and R. Okay. Here it is Rg, R1. The voltage is 1 volt. Okay, another galvanometer, the same galvanometer, R2. Okay, R2. The voltage range is 2 voltage. Again, it is Rg. Full scale deflection they mentioned for Ig. Both the cases I think Ig. Because about the second galvanometer, nothing is mentioned about the current. It means that the same current is going through the galvanometer. Okay, now frame the equation and solve the equation for the resistance of the galvanometer. I think it is in terms of the value R1 and R2. Okay, it may come under the value R1, R2 and V values. Okay, for a simple galvanometer conversion into voltmeter, no, we know the formula V equal to Rg plus R into Ig. Okay, so the first for this first case and second case. For first case, 1 voltage equal to Rg plus R1 into Ig. In second case, it is 2 voltage equal to Rg plus R2 and Ig. So we need to, what is that? Find Rg value. What shall we do? Simply do dividing. Division. We do division, what happens? Ig cancel. 2 voltage, sorry, only voltage get cancel. So 1 by 2 will come. So 1 by 2 Rg plus R1 divided by Rg plus R2. Then rearrange. Rg plus R2 equal to 2Rg plus 2R1. Okay, bring this 2R2 to the left hand side, Rg to the right hand side, and Rg and 2 get cancelled. Is that right?
Yes.
Then Rg equals to R2 minus 2R1. So this is the solution. The value of Rg must be equal to R2 minus 2R1. So that this kind of conversion will be achieved. galvanometer of resistance G, they have mentioned it is clearly as G, converted into voltmeter. So G is connected with voltmeter means we need R, series resistance R. The current
Yes.
through galvanometer is IG, that's all. Okay, and G can be converted into voltmeter of range V by connecting R in series with it. How much resistance will be required to change from V by 2 voltage? Then what is the value of R? So next, what they are connecting now, the galvanometer with an unknown resistance R dash. So that achieving here it is voltage V, it is V by 2. That's all.
Okay.
Same question in the the thing is the previously value R1 and R2 are given. We found RG. In this case, we are going to find this second resistance R dash.
Okay. Okay.
So we need to find R dash. Do you understand?
Yes, sir.
So how much resistance will be required to change the range from 0 to 2 voltage, 0 to V by 2 voltage? So first to find equation 1 and equation 2. Here Ig is not mentioned, it means it is constant. Rg also constant. Ig constant, Rg constant. That's all. Then frame the equation. First equation is V equals to Ig Rg plus R. Then second equation V by 2 equal to Ig Rg plus, we don't know, R dash. That is what we are going to find. Again, divide the equation. Divide the equation. Then V get cancelled. So 1 divided by 1 by 2 equal to Ig also cancelled. Rg plus R divided by Rg plus R dash. We need R dash only. Take this 2 to the numerator. 2 equals to Rg plus R divided by Rg plus R dash. Rearrange it. 2Rg plus 2R dash equal to Rg plus R. So Rg and 2 get cancelled. Therefore, 2R dash equal to R minus Rg.
Right.
R dash equal to R minus Rg divided by 2. So this is the required value of R dash. This kind of circular coil, two circular coils kept in different manner. No, we need to find the total magnetic field at a given point. See here, the point O is given, and we are going to find the total magnetic field at the point due to the currents in the two circular coils, and their orientations are different. So two very small identical circular loops, the radius are same. It means that identical loops having equal currents placed vertically with an axis perpendicular. Find the magnitude and direction of the magnetic. See, in this case, circular coil is kept in this particular coil 1. No, the current is what is that? It is flowing in one particular direction. You just use your right hand curl rule. See, when we use right hand curl rule, what happens now? Right hand curl rule. In this particular case, the direction of magnetic field must be towards the coil. In this particular case. The direction of the magnetic field towards the coil, you just take this as B1. Okay, and this particular case, it is again the curled fingers. The curled fingers will represent the direction of current. The thumb represents the direction of magnetic field. Therefore, in this particular direction, the magnetic field is upwards, B2. You understand?
Yes.
So B1 is in the left side direction, B2 in the upward direction. See, the two coils are identical and the currents are equal and the distance also same. Here it is x and here it's also. Therefore, the magnitude of the two cases are same. The magnitude of the magnetic field are same.
Yes.
Circular coil formula. We know the circular coil formula B equal to mu naught I divided by 2R. See, on its axis, right, it is not 2R. 2R square plus x square power 3 by 2. Is it right?
Yes. Yes, sir.
We'll check it. Check the formula also. We forgot the formula. Circular coil formula. On axis, mu naught I so 2 pi and 2 cancel mu naught I a square they mentioned. I so this one mu naught I r square. R square must be there, right? R square.
Yes.
So the radius r square. And about the radius, is it mentioned? So they mentioned it is identical. Therefore, both the cases we take r
R.
square. R and R only.
Okay.
See now, in this kind of case, the total magnetic field is the vector sum of the two magnetic fields. Vector sum. See, the magnitude are same. The magnitudes of the two cases are same. The value is like this. Okay, value is the same, but the magnitude are same and angle between the two vectors is 90 degree. In this case here it is 90. So go for Pythagoras theorem. For this particular case, we need to go for Pythagoras theorem. Therefore, B total is equal to B1 square plus B2 square inside the square root. See, for this case, the two numerical values are same. The magnitudes are same. Therefore, the value is B into root 2. B into root 2. So the value is mu naught I r square divided by 2r square plus x square for 3 by 2 into root 2.
Yes.
This is the answer. This is the answer, the scalar form. And they have also asked the direction. Direction. We know direction is, it is nothing but the tan of the angle. Thus, this is the direction of total magnetic field. So we need to go for the rectangular component, and in case of the opposite side and adjacent side, if they are equal, it means the angle is 45 degree. That's all. Because the vertical component is B2 divided by the horizontal component, it is B1. Both are same, it is 1 only. Therefore, theta 45 degree. In case of 45 degree tan, the answer is 1. So the angle is 45 degree direction.
Okay.
So We'll see this one, question number 47. Question number 47, it is having different formula. Previous cases, circular coil on its axis, but here the circular coil on its center. Okay. And again you apply, yeah, center,
mu naught I
because
by
the
2
question, mu naught I by 2R. The question, we have to draw the diagram, okay, the vector symbol. See here, it is downward. It is in this case curled finger. The magnetic field due to Q is in the right side direction. BQ is the right side direction. In this direction, BQ, it is in this direction. BP, it is in the upward direction. BP in upward direction. And here the magnitudes of the two coils, the magnitudes of the two magnetic fields may not be same because the currents are I and 3I, root 3I. So P carries current I, Q carries current root 3I. So the currents are not same. Therefore, the magnetic fields are not same. Now you will not get 35-degree angle. So 45-degree angle. The angle will be something different. Okay. So first we'll go for the magnitude. Magnitude is square root of BP square plus BQ square. Here also, because the angle between the two vectors 90-degree. Angle is 90-degree and the resultant is not 45-degree. So we need to calculate BP. So tan theta. That we will see later. Sorry. Okay. B, magnitude of BP. It is mu naught I divided by 2R. And the identical coil, since identical, the resistor, the value R is same. Radius is same. BQ, it is equal to mu naught root 3 I divided by 2R. Okay, you just insert them and take the common terms outside of the square root. So B equal to mu naught I divided by 2R whole square, mu naught root 3 I divided by 2R whole square. Take the common terms outside. Mu naught I, mu naught I, 2R also taken outside. So it is simply 1 only. Here it is 1. Here it is root 3 squared. So root 3 square is 3. 3 plus 1, 4. So you will get the root of
mu naught I by
equal to, yes, 2. So mu naught I by R. That's all. This is the answer. And about the angle theta. Theta is nothing but tan inverse of vertical. What is that? The horizontal, sorry, vertical axis, BP. BP divided by BQ. Okay, here BP is mu naught I by 2R. It is mu naught I divided by 2R. Therefore, it is tan I 1 by root 3. What is 1 by root 3? Tan of 1 by root 3. Tan inverse of 1 by root 3.
1 by root 3.
Is it 30-degree?
Yes, sir.
So 0, 1 by 2, 0, root 3 by 2. Therefore, 1 by root 3, 30-degree. So that theta is 30-degree with the horizontal. Okay, horizontal right side direction. Here also it is 45-degree with the horizontal, the left side direction.